Depletion of the world's mineral energy reserves and continued environmental pollution have become global issues. The search for new renewable energy sources is urgent. Lignocellulosic biomass is the richest and cheapest renewable resource on Earth, with up to 100 billion tons of lignocellulosic biomass produced annually by photosynthesis worldwide, 89% of which is not yet used. Lignocellulosic biomass includes cellulose, hemicellulose, and lignin. This video will mainly talk about lignin and catalytic treatment. Lignin is a complex class of organic polymers that form important structural materials. In chemistry, lignin is a cross-linked phenolic polymer and belongs to an aromatic polymer group. The xylem of vascular or woody plants contains large amounts of lignin, which allows the xylem to maintain a very high stiffness in order to support the weight of the entire plant. In 1819, Henri Braconnot, a French chemist, was the first to discover that lignocellulosic biomass treated with sulfuric acid could be hydrolyzed to sugar. The hydrolyzed sugar could then be processed through fermentation to form ethanol. The first commercial ethanol production began in Germany in 1898. There are four main processes for the catalytic conversion of lignin biomass to biofuels, which are catalytic thermal cracking, catalytic hydrolysis, catalytic oxidation, and catalytic hydrogenolysis. Catalytic thermal cracking was developed from the earlier common thermal cracking. The molecular sieve catalyst is preheated to 200 to 300 degrees Celsius under anaerobic or anoxic conditions, and then lignin is gradually added to the said molecular sieve catalyst for the catalytic cracking reaction at a temperature of 500 to 800 degrees Celsius, as well as in a protective atmosphere of inert gases, making use of the heat energy to break the chemical bonds of the biomass macromolecules, and reactions such as bond breaking, isomerization, and polymerization of the small molecules take place, and the reactions are completed. At the end of the reaction, the products of catalytic thermal cracking of lignin are separated to obtain liquid, gas, and solid products. Catalytic hydrolysis uses either acid or base catalysts for lignin hydrolysis. Morphologically, acid catalysts include liquid acids and solid acids. Acidic ionic liquids, as a typical liquid acid, were widely used in the early exploration of lignin depolymerization. For example, in recent years, the application of formic acid in the catalytic hydrolysis of lignin has attracted more and more attention, and formic acid has a very good effect on the hydrolysis of organ-soluble lignin, and it can be used to obtain 30% biooil yield, which contains 10%-12% of monophenolic compounds, under the condition of supercritical water at 300 degrees Celsius. It can get a 30% biooil yield at 300 degrees Celsius under supercritical water conditions, including 10%-12% of monophenolic compounds. The common alkali catalysts are lithium hydroxide, potassium hydroxide, sodium hydroxide, etc. They are generally dissolved in solvents for homogeneous catalysis during the lignin hydrolysis reaction. When a lignin hydrolysis reaction is carried out, they are generally dissolved in the solvent to achieve homogeneous catalysis. The catalytic effect of sodium hydroxide on the hydrolysis of lignin is significant. Within a certain range, the more alkaline the catalyst is, the higher the conversion of the raw material and the higher the selectivity of the aromatic compounds. Catalytic oxidative depolymerization of lignin can produce aromatic compounds containing various functional groups under mild conditions. Depending on the principle of catalytic oxidation, they are divided into electrochemical oxidation, photocatalytic oxidation, and chemical oxidation. Electrochemical oxidation requires an electrode to provide the energy required for the oxidation reaction. When copper-carbon is used as the electrode, the lignin side chain structure is oxidized, and low molecular weight aryl compounds are produced. Photocatalytic oxidation requires light conditions, and ultraviolet light has been shown to be effective in the catalytic degradation of high-boiling alcohol lignin reactions. Chemical oxidation is relatively simple and only requires the addition of a catalyst to catalyze the oxidation. The catalytic oxidative depolymerization of lignin significantly reduces the energy barrier for the breakage of the main chemical bonds of lignin, thus realizing efficient depolymerization of lignin. Catalytic hydrogenolysis of lignin refers to the process in which lignin molecules break their ether bonds in a reduction reaction under the action of a metal catalyst, and hydrogen replaces the departing heteroatoms or groups to produce a small molecule product. In terms of the types of catalysts, they mainly include precious metal catalyzed hydrogenolysis, transition metal catalyzed hydrogenolysis, and bimetallic catalyzed hydrogenolysis. Precious metals are widely used in the catalytic hydrolysis of lignin because they not only have superior hydrogen adsorption and dissociation capabilities but also catalyze hydrogenation and hydrolysis reactions. The most commonly used precious metal species are lead, ruthenium, and rhodium, while the carriers include activated carbon, solid acids, and solid bases. Precious metal catalysts have good catalytic hydrolysis effect, but the cost is too high, whereas transition metal catalysts are much cheaper and also have good catalytic hydrolysis performance. The most commonly used transition metals are nickel, copper, and iron. It has also been found that some specific bimetallic catalysts have synergistic catalytic effects and perform well in lignin hydrogenolysis. For example, Niau catalysts. 4 advantages of lignin. First of all, lignin biomass is an effective biofuel that can reduce fossil fuel dependency. Secondly, lignin biomass is a cheap raw material with abundant reserves. Thirdly, the use of lignin produces much less greenhouse gases than fossil fuels. Fourthly, lignin has a high conversion efficiency of up to 90%. 4 disadvantages. First of all, lignin is difficult to store and requires proper temperature and moderation, otherwise, it will burn on its own. Secondly, lignin is large in size, difficult to transport, high transport costs. Thirdly, the lignin catalytic process is too long. For future suggestions, in order to explore efficient catalytic depolymerization systems for the special structural characteristics of lignin, establishing optimal hydrogen-producing bacteria for the co-degradation of biomass wastes is needed. Secondly, there is also an urgent need to develop appropriate catalytic technologies to convert lignin from low-quality and low-value waste products to high-quality and high-value chemical raw materials. Last but not least, the search for an efficient catalyst that can increase the conversion of lignin with low energy consumption is expected to be found in the future. This is the end of the video presentation. Thank you.